This is lesson 13 of Calc 2 on partial fractions. And this is a technique which is often very useful for integrating what are called rational functions. A rational function is a quotient of polynomials. So you have some polynomial in the numerator, some polynomial in the denominator. So n of x and d of x are polynomials. And the first step in partial fractions is the following. If degree of n of x, the numerator, is greater than or equal to the degree of the denominator, then we divide. And you can write n of x over d of x as some polynomial plus two other polynomials, n1 of x over d1 of x, where the degree of n1 is now strictly less than the degree of d1. So you can always, by long division of polynomials, write this as a polynomial plus something where this has, the numerator has smaller degree than the denominator. Step 2 is to factor the denominator. And in principle, sometimes it's hard to do, but it's not just in principle, it's in principle. You can always factor d1 into linear and quadratic factors. Sometimes you get a quadratic factor and it doesn't factor anymore. But you can always reduce everything to a linear and a quadratic factor. And step 3, let's consider first the special case where the denominator is a product of distinct linear factors. Let's just write it as x plus a1, x plus a2, up to x plus ak. And then it's always true that you can write this rational function, the integral of that rational function, as something of the form a1 over x plus c1, a2 over x plus c2, ak over x plus, this should be ak's, ak, the integral of all this. And this is just a sum of logarithms. So this is the whole idea of partial fractions. And really the best way to see what's going on is to look at some examples. So suppose we have the integral of, just make up some numbers, 7x plus 2 over x squared minus 5x plus 4 dx. So the numerator has degree 1, the denominator has degree 2. We don't have to do any long division. The denominator factors. X squared minus 5x plus 4 is equal to x minus 1 times x minus 4. So by the theorem on partial fractions, we can write this as something in the form a over x minus 1, I'll just write b, and b over x minus 4. So there exist numbers a and b for which this is true. How do we find them? Well, we can cross multiply. So this is a times x minus 4. I'm going to put everything over this common denominator, plus b times x minus 1. So this is a plus b times x minus 4a minus b, or minus the quantity 4a plus b. This is x squared minus 5x plus 4. So these two fractions have the same denominator, so the numerators are equal. So the coefficient of x is 7, and the coefficient, the constant term, which is minus 4a minus b, is 2. If I add these equations, I get minus 3a equals 9. So a equals negative 3. And if a is negative 3, b is 10. So 7x plus 2 over x squared minus 5x plus 4 is equal to minus 3 over x minus 1 plus 10 over x minus 4. So if we integrate with respect to x, the integral of this first term is the natural log of x minus 1, and the integral of the second term is 10 times the natural log of x minus 4. And we found the answer. That's correct. So this was the special case when the denominator is a product of distinct linear factors. We also have the special case when the denominator is linear factors, but powers of the linear factors. And in that case, this rational function can be written as a sum of partial fractions. If you have x plus a1 to the L1, you're actually going to get L partial fractions. X plus a1, x plus a1 squared, x plus a1 to the L1, and so on. So you'll have, if you have x plus a1 to a power, then you have, if the power is L, then you'll have L partial fractions. And again, you need to look at an example. This is example 2. We have the integral 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x dx. So the degree of the numerator is 2, the degree of the denominator is 3, which is bigger, so we don't have to do any long division, but we do have to factor the denominator. x cubed plus 2x squared plus x. We can factor out an x. We factor out an x, and then we see this actually factors. This is x times x plus 1 squared. So we have two linear factors. So this rational function, 5x squared plus 20x plus 6 over x cubed plus 2x squared plus x, we're going to have one partial fraction from the x, and from the x plus 1 squared, we're going to get two partial fractions, an x plus 1 and an x plus 1 squared, for some numbers a, b, and c. How do we find these numbers? Again, let's put it over a common denominator. So we get a times x plus 1 squared plus bx times x plus 1 plus cx. So if you equate the numerators, you have a times x plus 1 squared plus bx times x plus 1 plus cx equals 5x squared plus 20x plus 6. Now, we can solve this in a couple of different ways. We could expand this. This would be a quadratic polynomial equal to this quadratic polynomial, and we equate the coefficients. Or we could say, well, let's take, for example, x equals 0. If you plug in x equals 0, this becomes 0, this becomes 0, this and this becomes 0. What we get is a equals 6. So by just plugging in x equals 0, we found that a is equal to 6. Suppose we plug in x equal -1. So x plus 1 is 0. So this is 0, this is 0. This becomes minus c. When x is -1, you get 5 minus 20 plus 6. That's minus 9. So c is equal to 9. So we found a and c pretty quickly. What about b? Well, let's just take a small number. Let's maybe take x equal 1. When x is equal to 1, you get a times 2 squared, 4a, plus 2b, plus c equals, when a is equal to 1, 31. Of course, a is 6, so this is 24, plus 2b plus 9 equals 31. So 2b plus 33 equals 31. 2b equals -2. So b equals -1. Perfect. So this expression we're integrating is 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared dx. So this is 6 times the log of x minus the log of x plus 1. If you integrate this, you get minus 9 over x plus 1 plus a constant. And that's the answer. Yeah. The last special case we're going to consider is when we're integrating something and the denominator involves a quadratic factor. So for every quadratic factor, which doesn't itself factor, you get a partial fraction where now the denominator is that quadratic and the numerator is linear. So we have linear numerator and a quadratic denominator. So this is, for example, this is example 3 in the section. The integral of 2x cubed minus 4x minus 8 over x squared plus x squared plus 4 dx. The numerator has degree 3. The denominator has degree 4. If we factor the denominator, x squared plus x times x squared plus 4, the first term factors into x times x plus 1, but the second term doesn't factor. So we have two linear factors and an irreducible quadratic. So 2x cubed minus 4x minus 8 over x squared plus x squared plus 4, we're going to have three partial fractions. The linear factor x gives us a partial fraction a over x. The linear factor x plus 1 gives us a partial fraction b over x plus 1. The quadratic factor x squared plus 4 gives us a factor with this quadratic in the denominator and something linear in the numerator. So we have to find these four numbers, a, b, c, and d. Again, we can put it over a common denominator. We multiply a by x plus 1, x squared plus 4. We multiply b by x times x squared plus 4. And we multiply cx plus d by x times x plus 1. So equating the numerators, we have a x plus 1 times x squared plus 4 plus b x times x squared plus 4 plus cx plus d x times x plus 1 equals 2x cubed minus 4x minus 8. This numerator has to equal this numerator because the denominators are the same. So we could, again, expand this. We get a cubic equal a cubic and equate the coefficients. But again, it might be a little bit quicker, at least for some of the coefficients, to choose good values for x. Like if we let x equal 0, here we get 4a. A times 1 times 4. This is 0, this is 0. This is 0, this is 0. Equals minus 8. So right away we get a is negative 2. If we let x equal minus 1, so x plus 1 is 0. This is 0. This is 0. So when x is negative 1, we get minus b times 5, minus 5b. And when x is negative 1 over here, we get minus 2 plus 4, that's 2, minus 8 is minus 6. Let me just double check that. If x is negative 1, this is 0. This is, yeah, when x is negative 1, this is 5 minus 5b. Minus 2 minus 8 is minus 10 plus 4 minus 6. So I'm a little bit skeptical about that, so I'm just going to review what I did to make sure there's no mistake. So we have this numerator, 2x cubed minus 4x minus 8. The denominator is x. I wanted this to be the example that's in the book. In the book, this is x minus 1. X minus x. And this is x squared minus x. And this factors into x times x minus 1 times x plus 4. So x squared minus x is x times x minus 1. And so this is x minus 1. And this is dx, and this is cx plus d. And x minus 1. What I had done was correct, but it wasn't the right double. So we get a times x minus 1, x squared plus 4, dx x squared plus 4, cx plus d, x times x minus 1 equals this. If you let x equal 0, I get minus 4a equals minus 8. So a is equal to 2. By that x equal 1, this is 0. This is 0. So when x is 1, I get 1 times 5, I get 5b equals, when x is 1, 2 minus 4 is minus 2 minus 8 is minus 10. So b is minus 2. All right, that was quick. I found a and b easily. For other values, there's nothing quite so obvious to pick. Suppose I let x equal minus 1. If x is minus 1, I get minus 2 times 5 minus 10a. Minus 1 is 5 minus b minus 5b. When x is minus 1, I get plus minus c plus d, or d minus c, times minus 1 times minus 1, minus 1 times minus 2, which is 2, equals minus 2 plus 4, 2 is minus 6. So if a is equal to 2, this is minus 20. If b is equal to negative 2, this is plus 10 plus 2d minus 2c equals minus 6. So I get an equation that says minus 10 2d minus 2c equals 20 minus 16 equals 4, and d minus c equals 2. Well, That's one relation between D and C. Sometimes problems are more complicated than I might like. So that's what I got when I let x equal to 1, minus 1. Oh, well, suppose I let x equal 2. If I let x equal 2, I get 8a, and x is 2. 4 plus 4 is 8 times 2 is 16, plus 2c plus d, and x is 2, this is a 2, equals 2 times 8, 16 minus 8 equals 0. And a is 2, so this is 16, and b is negative 2, and this is 4c plus 2d equals 0. So 4c plus 2d equals 16, or if I divide by 2, 2c plus d equals 8. And my other equation was minus c plus d equals 2. So if I subtract, I get 3c equals 6, or c equals 2. And b minus c is b minus 2 equals 2. So d equals 4. All right, well, so what is our partial fraction decomposition? We have that 2x cubed minus 4x minus 8 over x squared minus x times x squared plus 4 is equal to a over x plus b, b is minus 2, minus 2 over x minus 1 plus cx, c is 2, plus 2x over x squared plus 4 plus d plus 4 over x squared plus 4. This is my partial fraction decomposition. And then we integrate. We integrate term by term. The first term is 2 times the log of x. The second term is 2 times the log of x minus 1. When we integrate this, we make a substitution, u equals 2x, and we get the log of x squared plus 4. And here, let me do that one separately, the integral of 4 over x squared plus 4 dx. So this is going to be an arctangent. Suppose I make a well, let me factor out a 4 from the numerator and the denominator. So this is the integral of x over 2 squared plus 1 dx. Multiply this out. X squared over 4 multiplied by 4, you get this. If we let u equal x over 2, so x is 2u, dx is 2 du. When we substitute, we get the integral of u squared plus 1, 2 du. This is 2 times the arctangent of u, which is 2 times the arctangent of x over 2. So we get this is the arctangent x over 2 plus the constant. Ooh. Yeah, that's the picture. It took some work. All right, so this is the last technique of integration in the course. What we will be doing after this, well, there's something called improper integrals that we'll talk about. And then we have two completely new subjects, infinite series and ordinary differential equations. That will take out the second half of the course. Okay, that's all for today.